Welcome to Section 7, Lesson 10. So far we have learned to test rational candidates and divide polynomials cleanly. Today we put it all together. The goal is to find every root of a polynomial, real and complex, and write down its complete factorization. By the end you will have a procedure that works on a cubic, a quartic, or anything higher. A polynomial of degree n always has exactly n roots in the complex numbers counting multiplicity. That is the fundamental theorem of algebra. It tells you when to stop searching. Once you have n roots in hand, you have them all and the factorization is complete. The strategy chains three tools you already own. List rational candidates with the rational root theorem. Test each one with synthetic division. When the running quotient drops to a quadratic, finish the job with the quadratic formula or simple factoring. The two examples today take that strategy to the finish line. The first is a cubic with three real rational roots. The second is a quartic that hides two complex roots inside a quadratic factor, and that is where the imaginary numbers earn their keep. The fundamental theorem of algebra says a polynomial of degree n has exactly n roots in the complex numbers counting multiplicity. Three quick polynomials make that promise concrete. One quadratic, one cubic, one quartic, side by side with their roots drawn in. The quadratic x squared minus 5x plus 6 factors as x minus 2 times x minus 3. Two roots, both real, sitting on a number line at 2 and 3. Degree 2 roots, the count is exact. The cubic x cubed minus 1 is harder. One root sits at x equals 1 on the real axis. The other two are complex conjugates on the unit circle at angles plus and minus 120 degrees. Three roots total for degree 3, but only one of them is real. The quartic x to the fourth minus 1 gives four roots that line up like compass points. Plus and minus 1 on the real axis, plus and minus I on the imaginary axis. Real roots in cyan, complex in pink. Degree 4, four roots, the theorem holds. First worked example, find every root of p of x equals 2x cubed minus 3x squared minus 11x plus 6. The curve is plotted underneath so you can see where the roots ought to live. The curve crosses the x-axis 3 times, so we expect 3 real roots. And the fundamental theorem says that is all of them. Build the rational candidate list. The constant term is 6, so the numerator candidates are plus or minus 1, 2, 3, 6. The leading coefficient is 2, so denominators include 2, which adds plus or minus 1/2 and plus or minus 3/2. 12 candidates total to scan through. Try x equals 3 first. Run synthetic division with 3 on the left. Bring down the 2. Multiply 2 times 3 is 6. Add to negative 3 to get 3. Multiply 3 times 3 is 9. Add to negative 11 to get negative 2. Multiply negative 2 times 3 is negative 6. Add to 6 and the remainder is 0. 3 is a root. Drop a dot at x equals 3 on the curve and slide x minus 3 into the factor list on the right. The bottom row of the table O gives the quotient 2x squared plus 3x minus 2. Now the polynomial has dropped from degree 3 to degree 2 and the rest is just a quadratic. Factor the quadratic. 2x squared plus 3x minus 2 splits as 2x minus 1 times x plus 2. You can verify by expanding the product term by term or by the quadratic formula. Both routes lead to the same pair of factors. The two new roots are x equals 1/2 and x equals negative 2. Two more dots glow on the curve at those x values, and the matching factors slide into the list. We now have all three roots and three linear factors. Putting everything together, p of x equals 2 times x minus 3 times x minus 1/2 times x plus 2. The leading 2 stays out front because that is what the original polynomial started with. 3 roots found, fundamental theorem satisfied, and the cubic is fully factored. Second worked example. Find every root of p of x equals x to the fourth minus 16. The polynomial has degree 4, so the fundamental theorem promises exactly 4 roots. The number line below is where the real ones will land. The candidate list is built from the divisors of 16 plus or minus 1, 2, 4, 8, and 16. The leading coefficient is 1, so no fractional candidates this time. We try them in order of size, smallest first. Try x equals 2. Synthetic division with coefficients 1, 0, 0, negative 16 gives a bottom row of 1, 2, 4, 8, 0. Remainder 0, so 2 is a root. The quotient is x cubed plus 2x squared plus 4x plus 8, and a real root dot lands at x equals 2. Try x equals negative 2 on that quotient. The synthetic division row gives bottom values 1, 0, 4, 0. Remainder 0 again. Negative 2 is a root. A second dot lands on the number line, and the new quotient is just x squared plus 4. That is degree 2, and we are nearly done. Set x squared plus 4 equal to 0, which means x squared equals negative 4. There is no real number whose square is negative, so the search for real roots ends here. We need to step off the real number line and into the complex plane to find the last two roots. Add a vertical imaginary axis and the number line becomes a complex plane. The square roots of negative 4 are plus and minus 2i, and they sit on the imaginary axis at plus and minus 2. Two more dots in pink exactly opposite each other, completing the conjugate pair. Putting it all together, p of x factors as x minus 2 times x plus 2 times x minus 2i times x plus 2i. 4 linear factors, 4 roots in the complex numbers, 2 on the real axis and 2 on the imaginary axis. The fundamental theorem checks out for degree 4. 3 takeaways close the lesson. Each one is something you can use the very next time you face a polynomial and need every root. Every degree n polynomial has exactly n roots in the complex numbers, counting multiplicity. That is the fundamental theorem of algebra, and it tells you when the search is complete. Once your factor count matches the degree, you are done. Chain rational root theorem, synthetic division, and the quadratic formula in that order. Use the theorem to list candidates. Use synthetic division to confirm them and reduce the degree. When the quotient is quadratic, switch to the formula or simple factoring. The pipeline never breaks. Complex roots come in conjugate pairs whenever the coefficients are real. If a plus bi is a root, then a minus bi is also a root. That symmetry is why the imaginary roots in example 2 appeared as plus and minus 2i, mirror images across the real axis.